In this video, I'm going to define the gradient function and the gradient vector, and I'm going to compute an example. From the last video, we know how to compute the directional derivative of a surface function, f, if we have a point and a unit vector. Here's what's interesting. This formula could be rewritten this way, as the dot product of two vectors. It's easier to see how to get from the second line to the first line, but we could certainly rewrite this way if we wanted to. The second vector we know already, that's u, but the first vector is new. Let's name it. That symbol is a nabla, that upside-down triangle, but we say the gradient of f evaluated at x0, y0. Here are some facts. The gradient of f is a function of two real variables, just like f. The outputs of the gradient function are vectors, not numbers. The components of the vectors are computed using the partial derivatives of f. This output vector is super useful for computing directional derivatives. We call nabla f the gradient function, and nabla f evaluated at x0, y0 we call the gradient vector at that point. Here's an example. If f of x, y is equal to sine of x minus y, find a formula for nabla f as a function of x and y. Next, compute the gradient vector of f at the point pi, 0, and compute the directional derivative of f at pi, 0 in the direction 0, 1. Here we go. I know that the expression for del f is a vector, and the two components are just the partial derivatives. I can use the chain rule to get those partial derivatives, and I plug them into the formula. Done. If I want the gradient vector at a single point, it's as simple as plugging in the x and y values that I am given and simplifying. I get the vector -1, 1. Done. Finally, I can use this vector and dot product it with the direction vector that I was given, and I can determine that if I'm standing at the point pi, 0, and I walk in the direction 0, 1, I am going uphill at a rate of 1.